This is ScioVirtual Day 6 on memory. In the previous lessons, we talked about MOSFETs. And to remember, MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. But it's just a device that, for our purposes, allows us to have a switch. So with the gate, we can use to turn on or turn off the ability for current to flow from the drain to the source or from the source to the drain. And we had two types of MOSFETs, and combining them got us CMOS logic, complementary MOS logic. And from CMOS, we were able to get digital logic gates. And we found that to get a NOT gate, we only needed two logic gates. And to get NAND and NOR gates, we needed four logic gates. And so let's just real quickly go through the demo of those. Um, I'll pull those up. So here's the NOT gate. When A is off, notice that our PMOS over here is on. The wire is connected and current can flow. We effectively have a short circuit. The NMOS is off, right? The NMOS at the bottom, that gate is not allowing any current to flow because for an NMOS, low gate voltage means the gate is closed. Whereas for a PMOS, low gate voltage means the gate is open. We found that when we turned on the gate, we create an inverter, right? On gets us an output of off, off gets us an output of on. For the NAND gate, we can sort of create a similar effect due to the gates by wiring two PMOS in parallel and two NMOS in series. And for the NOR gate, two PMOS in series, two NMOS in parallel. Okay. And notice for all these, the NMOS is the one that goes to ground, and the PMOS is the one that goes to the high voltage. It could be 5 volts, could be 3.3 volts, it's whatever represents a logical one in your circuit. And then from these NOT, NAND, and NOR, you can make more complicated gates like our XOR, our AND, OR, and all the full combo of gates. Yeah, XOR, XNOR, and OR. Okay. Now, today, what we want to talk about is the ability to have memory in circuits. And that ability comes from really primarily this circuit, which we call the SR latch. First thing I want to point out, this is not a connection of wires. They're just crossing, but they're like kind of overlapped, right? They're not actually touching. So that's not a node. This is a node. The wires actually connect up at the right there. But in this middle, they don't connect. So let's go through what the circuit does. Well, we have NOR gates. So neither A nor B can be 1 if we want an output of 1. In other words, both of the inputs have to be 0 to get us an output of 1. So if R equals 1 and S equals 0, what's the output? Well, if R equals 1, that means that we are in one of these three situations, right? And all three of those situations lead to an output of 0. So we know we have a 0 there. If we have a 0 there, we can trace that wire down here. So we have a 0 here as well into the other NOR gate. So this NOR gate has two inputs of 0. I'll do this in green. That means it's outputting a 1. So there's a 1 right here. And we can trace that one back up. Again, these wires are not connecting. And there's a 1 right here. And so the situation that we're in is actually, I'll do this in red, this bottom situation, which indeed is 0. So we started with the top gate, got the output, went to the gate at the bottom left, got the output, and then we didn't have to take this wire that I'm tracing in red back, but we did just to check consistency. The net effect, I'll go through that one more time just so we're clear. Well, we have Q equals 0 at the top. Q represents output. Q is our general symbol for output. And then the bottom gate gives us 1. Q prime or Q with a bar on top of it represents not Q. And so in general, this output will be the inverse of Q. So when we do R equals 1, Q becomes 0. That's the moral here. Let's now trace the other situation. We have a 1 on the bottom here. So that means that we're in one of these three situations again. And so 0 is definitely our output here. Trace that wire back. That means 0 is the output here. And if this gate, top gate, has two zeros as its inputs, that means its output must be 1. Trace the 1 back just to check consistency. 1, 1 indeed gives 0 as an output. So just to say that one more time, just so we're completely clear. The bottom gate has a 1, its output is 0. Trace the 0 back, the top gate output has to be 1. Trace the 1 back, everything is consistent. Okay. So now say in either of these situations, either this situation where we had R equals 0, S equals 1, or this situation where we had R equals 1 and S equals 0. Say in either of those situations, we turn the gate off. What's going to happen? Well, let's look at our graph here and do that. So let's say we started with S equals 1. Okay, we have a 1 here, we have a 0 here, we have a 0 here, and we have a 1 here. And now let's say, I'll do this in light blue, we're going to change this S into a 0. Okay, that's no longer a 1, this is going to be a 0. Well, the moment we turn S off, this 1 is still going to be a 1, right? So we have 1 and 0 going into this gate. And so that means our NOR gate is still going to output 0, right? And so there's still going to be a 0 here, and this gate is still going to output 1. So I encourage you to use this tool and see that for yourself. If we go and if I deselect S, indeed that's what happens. The circuit doesn't change, right? Now, what about when I hit R? Well, as we already saw, R makes the output here 0 and the output here at the bottom 1. So I'll annotate these as well. Well, when I turn R off, I'll do this in a different color. When I turn R off and make it a 0, that means this top gate is receiving 0 and 1, but that's still going to output 0. And so 0 is still going to be the other input to this gate, and this gate is still going to output 1. And so 1 is going to be up here, and that's still going to output 0. So it remains consistent. If I turn off R, indeed that's what happens. Changing R does not do anything, right? So I could have S and R equals 0. S is 0 right now, and R equals 0. And we're getting Q equals 1. But now I'm going to click S twice. And then I'm going to click R twice. I'm going to turn R on and then turn R off. Now notice we have the same thing. S equals 0, R equals 0. But now Q equals 0. So the same inputs to this circuit somehow give two different outputs. How does that make any sense? That's memory. That's how we define memory. You might hear the term hysteresis. That means the same thing. We're saying just knowing the inputs of the circuit at a given point in time is not enough to know the state of the circuit. You need to know its history as well, its memory. So this is called the SR latch, and it is the simplest memory circuit we have available. But we have a problem. What if both of the inputs are 1? So let's go through that back on the slides. These slides, again, just go through what happens when you turn off an input and establish that memory is a thing that happens, right? But there's a problem. So say both R and S become 1 at the same time, and then we turn something off. We turn them both off at the same time. The behavior is going to be unclear. So if we set them both equal to 1, you can trace this for yourself. I encourage you to do that. You get Q equals 0 and Q not equals 0. Okay, fine. There's no problems when you do that analysis. That's okay. That's all good. But now we need to figure out what's going to happen when we switch both R and S off at the exact same time. In other words, we have R and S that are 1 right now. We're going to change that instantaneously to R and S equals 0. Well, it depends on what gate we look at first. If we look at the bottom gate first, that means now this bottom gate is receiving 0 and 0. Again, we're still pretending this is 1 up here. We're not analyzing that yet. And so this gate's going to output 1. We're going to get a 1 up here. And then whether this is 1, or sorry, we're saying this is 0. So 1 or 0, 1 or 1 is the same thing, output 0. Okay, fine. Just to reiterate that, because I got a little jumbled in my words. The bottom gate receives 0, 0. So the bottom gate outputs 1, top gate outputs 0. What if we looked at the top gate first? Well, then the top gate's receiving 0, 0, so it should output 1. That means the bottom gate outputs 0. But these are two different outcomes. So what ends up happening is if I have an SR latch and I change R and S at the exact same time from 1 on both of them to 0 on both of them, I don't know what my output is going to end up being. It's metastability. We might end up with a 1 on the top gate output. We might end up with a 0 on the top gate output. It depends on whichever gate is faster. And in general, you don't know that. So in an SR latch, you avoid having RNS equal to 1. This is the motivation for the D flip-flop. Now, I'll be honest, this is not actually a D flip-flop that we're looking at here. This is called a gated D latch, but it is the same functionality, just the D flip-flop has an edge detection, whereas the gated D latch is simply just logical high detection. But that doesn't really matter. The point is this resolves the both being one at the same time problem. So let's just look at the demo. Notice again we have NAND and NOT gates here. So we're going to go to manual clock and reset it. Okay. So the clock input is going to be what enables the circuit to do something. And then the data input is what that something is. That's how I think about it. So notice right now the clock is off. Okay. Notice right now that the clock input set by this, the clock is off. If I do anything to data, notice how the outputs aren't changing. Nothing is happening, right? However, if I turn the clock on, now the output will reflect whatever changes I make to data. So clock off, we're remembering the previous state of the circuit. Clock on, we're recording data. Okay, this is still memory. Notice, if I have 0, 0, I can get an output of 1. But if I turn data on and then clock on and then clock off and then data off, now I have 0, 0 giving an output of 1. Just to say that again, we have 0, 0 inputs. We're getting an output of 1. If I do this, then this, then this, then this. Now I have 0, 0 giving us an output of 1. Okay? 2 different outputs for the same set of inputs. That is memory. But now there's no problem having both of these be 1 at the same time. In fact, that's how we store the state of a logical 1. So this is a gated D latch. The difference in a real circuit is a real circuit records at an edge instead of recording constantly while clock is high. It just records on the edge of the clock. This ends up being better, but when you need to synchronize tons of things together, because then you don't have to deal with, well, how long is it going to take during the high cycle? Am I going to get switching? You can just say, at this exact moment in time, once the switch actually happens, I will record data at that point and not after that point. So that would be the D flip-flop. This is the gated D latch, similar functionality. So what these blocks here, these are gated D latches, are D flip-flops, right? Notice we have data, that's the blue. The red is going to be the clock, right? Clock is the same as red. Or enable, clock and enable are kind of the same term here. And then you have Q and Q naught. Each of these can store a 1 or a 0, right? Q can be 1 or Q can be 0. But say I want to store a multi-bit number. Say I want to store the number 7, which in binary is 1, 1, 1, 1. Well, then I'm sorry, that's a complete lie. Say I want to store the number 15. Okay, there we go. Which in binary is 1, 1, 1, 1. Right? 1 plus 2 plus 4 plus 8, that's 15. Well, then I need 4 flip-flops, right? So I need this flip-flop to store 1, I need this flip-flop to store 1, I need this flip-flop to store 1, and I need this flip-flop to store 1. To do that, we wire all of their enable lines together. So the enable line, again, is what lets the flip-flop actually store data. That's this clock that I'm pulsing right now. We wire all of them together so that all 4 flip-flops record data at the same time. But their data lines come from different sources. So maybe one bit's coming from one location, other bit's coming from a different location. Okay. We call this a register. A register is a bunch of flip-flops together that can store a multi-bit number. You can think of a register like literally a multi-bit flip-flop. Okay. So let's just do an example. Given the bottom row here represents the different values of 3 of the data lines. The data lines are here, what I've drawn in red. At different points in time, given the state of clock where the bottom is low and the top is high, what will the final value of data be? Well, it's not going to record this because clock is low. So at this point, data is still whatever, the Qs are still whatever it was initially. It will record this. So Q at this point is going to equal 0, 0, 0, 1. The outputs, right? The Q's are the outputs. It's not going to, sorry, it will record the next one. So it's going to overwrite Q with 0, 1, 0, 1. And it will record the next one as well. It'll overwrite Q with 1, 1, 1, 0. But then it's not going to record the last one because that occurs when the clock is low. So the answer to this question is the final values of Q are this. This is the final state of the register, the final value it stores. Now, RAM, random access memory, is just a bunch of flip-flops, plus some extra machinery to coordinate the flip-flops. We'll talk about that when we get to the actual CPU. It involves a decoder and a multiplexer. But the moral is we need different registers to store different numbers. We can't just have a stack of a bajillion flip-flops because then we don't know where one number starts and the next number ends. So you typically have a bunch of 8-bit or 16-bit registers so you can store 8-bit or 16-bit numbers. Okay. So maybe in my code, I write X, Y, and Z equals X plus Y. Then in my memory, I'm going to have one register for X, one register for Y, and one register for Z. And my CPU is going to do something on the registers that store X and Y to get the right value in the register that stores Z. Okay. So when code gets turned into actual instructions for a computer, each thing, abstract thing in my code gets an address. And the CPU is just doing things to and from those addresses. We'll get to that next week. Now, this system of registers storing information with different registers for different parcels of information is called RAM, random access memory. There's nothing random about it. We call it random access memory because you can choose any register, register 0 or register 7, and they're equally easy to access. The reason this is important is because prior to this, memory was essentially on a tape. So if you think about a tape, if you want to access something at the end of the tape, you gotta pull a bunch of tape out, right? So it's not easy to access something late on the tape as it is early on the tape. So that's not random access because it's difficult to access later things as compared to early things. However, this is random access. I'm saying that in quotes because it's equally difficult to access any point within any register within RAM. So it's kind of just a data terminology, but that's what we use. And yeah, so this is just another statement of what this code does. We have registers for X, Y, and Z, and then maybe a register for machine instructions. That's von Neumann, and we'll get to that more in lesson 8. So that's not for today. Well, that's that. Thanks very much.